Okay, now we consider a loop, area 4 square meters, rotating about the z-axis, okay, with some unspecified frequency at this point, but then I'll specify an angular frequency of 100 pi radians per second, just as we had previously. Okay, the magnetic field is 0.005 Tesla times I. The area is 4 square meters. Frequency rotation is F. The normal vector is a function of time, because as the loop rotates, the normal vector rotates along with it. So what would an appropriate time-varying normal vector be for this situation? Well, we can go over here to a unit circle picture. And this unit circle has nothing directly to do with this 4 square meter loop of circle here. But if the normal vector is here at some time t, and of course we see the normal vector starting in the y direction, moving this way, but it doesn't necessarily start at the y-axis. So we're just going to assume a normal vector. And we're going to assume an angle theta from the positive x-axis, and that theta equals omega t. So effectively, we're starting this loop at a position where the normal vector is in the x direction, and that does correspond to the picture we have here. So here's the normal vector. As the loop rotates, the normal vector is going to rotate from the x-axis out toward the y-axis and around. So here's a normal vector. Theta equals omega t, where omega is the angular frequency. Now I haven't specified what that angular frequency is at this point, but I do down here. And it's going to be the same angular frequency we saw before, but now it's not the magnetic field that's fluctuating. It's the loop that's rotating and the orientation of the circle with respect to the fixed magnetic field that produces the changing flux. Okay, so the area vector, well, okay, if the normal vector is here at angle theta equals omega t, then what are the components of the normal vector? Well, it's going to be the cosine of the angle times I plus the sine of the angle times j, and that again is should be a second nature understanding. That's something you should understand immediately. If you don't, give it more thought. It needs to become that way. Okay, so the normal vector is this. That's a normal vector as a function of time. So now our area vector is the area 4 meters squared multiplied by the time varying normal vector. The flux then is the dot product, v dot the area vector. And without writing it all out, it should be clear that if I multiply 0.005 Tesla times I, or take the dot product, I'm sorry, of 0.005 Tesla times I with the area vector, the j component is not going to be, the result we get from the j component is going to be 0. The result we get from the I component is just going to be the 0.005 Tesla times the 4 meters squared times the cosine of omega t, which gives us our 0.02 Tesla times the cosine of omega t. Okay, so the EMF is going to be the derivative of this, okay? And the derivative of this flux is just going to be, well, derivative of the cosine of omega t is omega sine omega t. I don't know where I got omega cosine omega t, but I'm going to pause a minute and make a correction. Okay, made the correction. The derivative of the cosine omega t is the negative omega times the sine of omega t. I didn't write down the negative, and I wrote down a cosine instead of a sine because I was talking and not thinking, I guess. Okay, in any case, we have this being our EMF. Okay, now if the frequency is 100 hertz, or frequency is 50 hertz, then our angular frequency, well, 50 times around the reference circle is 50 times 2 pi radians. So we have 100 pi radians per second. And the result is the EMF is negative 2 pi times the voltage times the sine of 100 pi t. The omega being 100 pi here is going to give us, multiplied by the 0.02 is going to give us 2 pi. We'll still have the negative sign and so forth. Very straightforward. So now we ask the question, what if the resistance of the loop is 20 ohms? You haven't thought about this, you should. Okay, but if the resistance of the loop is 20 ohms, then the current is little I of t. Now we're going to use little I for time varying current. We're going to use capital I for a constant current. This is consistent with the textbook's notation. Just for clarity, if I'm talking about the I vector, I'm going to have an arrow over it. Or if you see it in a text document, it'll have a backward apostrophe I. And in most of the documents, whether text or otherwise, I'm going to have a backward apostrophe because those documents could be converted to text, and if I don't have the backward apostrophe, you might not know which I I'm talking about, okay? So, anyhow, the current is what? Just the EMF divided by the resistance. So, that gives us very, dividing by 20 ohms, we're going to have a 20 ohms in the denominator here. Dividing volts by ohms, we're going to get amps. The 20 in the denominator is going to, 2 is going to divide the 20, give us a 10. We're going to have this current, negative pi over 10 amps times the sine of 100 pi t. That would be negative, the amplitude would be about 0.3 amps. Okay. Now, how much power does it take to maintain that current? The power is going to be the current, which is in amps or coulombs per second, multiplied by the EMF, which is in volts or joules per coulomb. Joules per coulomb times coulombs per second gives us joules per second, giving us the result watts, confirming our calculation. So it's I times E, and when we multiply that out, I believe that we're certainly going to get a pi squared. 2 over 10 is 1 over 5, so we have pi squared over 5 times the sine squared, because we have a sine from each of these terms, of 100 pi t watts. And that's the power we need to maintain the circuit. And that's also the wattage dissipated as heat in this circuit.